Second part of lesson 2, ecological pyramids. Here is a screen capture of the assignment I've given you. It has a complete summary of this lesson on it after you've learned it. And we're just going to look at these 3 pyramids first. The pyramids of numbers suck. It is one of the most useless things to do is to count the number of animals at each trophic level. In generally, it will drop. You're going to have a million blades of grass, 700,000 rabbits, maybe 200,000 foxes, obviously not, and then maybe like one, I don't know, yeti in the area. It will generally go down, but counting critters really doesn't help much. The next one would be biomass. This one, there is no way you outweigh your food supply. Unfortunately, you leave behind far more poop than anything else. Something like 12 tons of it per human being by the time you reach adulthood. It is only in science fiction movies that a creature can burst out of a man's chest, hide in the ship, and an hour later weigh 800 kilograms. You cannot outweigh your food supply. Not even close. Your total weight of food you've eaten since birth is probably the weight of 100 human beings, and yet you still hold roughly the same weight. It's only energy that's really useful. So pyramid of biomass will convert to energy, but the trouble is sugar holds a lot more energy than protein does. So we're going to focus on energy of pyramids. Energy is one of the backbones of science. It's poorly understood by the public, and I'm going to drill this into your brain throughout the course so you're ready for grade 11, that you come armed with something you need to know by then. We can say energy is the ability to do work. It's a classic definition, doesn't tell you much. It is measured in joules. The old school measurement is calories, which you may be familiar with food. The difference between a calorie and a joule is the difference between like a pound and a gram. The calorie is a huge unit, a joule is a very tiny one. You eat a couple thousand calories of food a day, it's 10 million joules on average in North America. So 10 million joules is the same as a couple thousand calories. Most of you might weigh 50 to 100 kilograms. That would be 50,000 to 100,000 grams. You didn't suddenly get fatter. I just changed the unit to a tiny one. Give you an idea, 4 joules is needed to raise 1 gram of water. That would fit in a thimble, 1 degree Celsius. When you boil a cup of water, you bring it up by 100,000 joules of energy. So it's a very tiny unit. In formulas, it's kind of funny. The first formula you have ever seen in your life, E equals mc squared, typically put on a nuclear bomb, is Einstein's formula, and it will be the last one you study in high school. In grade 11 physics, you'll study these two. Energy due to a moving car is half of its mass times its speed squared. And if you want to know the energy you have when an object, say, falls and hits your head, you multiply it by mass, how much the gravity is on Earth, and its height. This one we used to do in grade 9 and grade 10. If you want to know how much energy went into heating, say, a bar of steel, you type in the mass, what it's made out of, and how warm it got. So if you wanted to learn these in grade 9, I'll teach it. It's dead easy. But by grade 11, you'll be using these 4 formulas. So I want you to get comfy with energy now. There's only a few kinds of energy that we've ever discovered. Gravity, moving, electromagnetic, which is like magnetism, electricity, light. Then there's heat, sound, elastic energy, and chemical. Living life is chemical energy. We don't store it in electric batteries in us unless you're an electric eel. It's almost all chemical. But it came to Earth as electromagnetic, or what's called radiant energy from the sun, and we built chemical energy with it. And what do we do with that energy? Well, we grow, we move, we heat up, we dump it out as waste from our body, and we store it on our body as well. It's only the stored energy on us that a predator can eat. And what we store is a fraction of what we take in by a long shot. We store very little of our food. Remember, by the time you reach adulthood, you've pooped more than 12 tons. So even if you got overweight, you've still excreted vastly more material than you kept on your body, unless you're Jabba the Hutt. Now, if we look at this is again another diagram, and it's showing where our body goes. This is 90% of our energy is here. Okay. 10% is on this woman's body. 90% of the energy of a human being goes to keeping us warm, running around, this little tiny sliver for growth, and keeping us warm here. And this amount went to making babies. Look at the poor little mouse. See this big wedge here? Okay, that's how much it takes the mouse to stay warm because he's so tiny. Look at the reptile. There's nothing. So poor little mouse is burning off out of the 90% of the energy it needs to stay alive. This huge chunk of it is just going to stay warm. So mammals waste energy like you wouldn't believe. So how much moves on each level? Well, we have to start with the plants. Let's do a little thinking here, what Einstein called Gedanken, thought experiments. This is the sunlight brightness. Look at the color of the plant, look at the color of the earth. Is the plant absorbing most of the light that hits it or reflecting it? And which color from the sun did it absorb and which did it reflect? Okay. The more it absorbs, the more efficient it is. The more it reflects, the more it's wasted. Is this plant sucking in more of the brightness than it's kicking back, or is it reflecting most of the light? Let's switch to infrared again. Plant chlorophylls like the red color and blue. They don't like green. How can I tell it doesn't like green? Because you see the green, it's spitting it back. If the plant was red, it means it's kicking the red light back at you. So under infrared, the color of light that plants want to do photosynthesis, look at their color. Are these plants reflecting the red light back to you, or are they soaking it up? You can use logic to come to this conclusion. Once again, look at this landscape. This is summertime. Here is grass under infrared. There are the leaves under infrared. That's the asphalt pavement here, and here are the trunks of the trees. Which surfaces suck up the light? Which surfaces are kicking it back? And do another little Einstein thought experiment. Walk barefoot across the grass and then onto the pavement. Where is the energy from the sun being sucked in? Do your feet and your eyes tell you which of these surfaces is eating the sunlight into thermal energy and which surface is just kicking it back? Well, it turns out the plants are quite bright, aren't they? So they're kicking back the sunlight. Look at it. Plants are kicking back 95% of the green light, 90% of the yellow, 70% of the orange. The red light, they were only kicking back 50%, and they were still bone white under red. So the plants are actually kicking back 99% of the light that hits them. Even the Cookie Monster eats more than 1% of the cookies in his mouth. So the plants waste it. Imagine I gave you 100 apples and you dropped all of them but one. That's how bad the plants are. So how do we calculate how 100 joules of sunlight winds up being only 1 joule of strawberry? You divide by 100, just move the decimal place over 2. So if you get a number like 11.7, just go bounce, bounce, and that's all that the plant stores. So plants are staggeringly wasteful on their energy, but it's coming in for free, isn't it? So the fact that plants are bright in color and cool to the touch means they are not absorbing much energy. This is something you don't have to study. You can rationally figure it out. Now, animals are actually better than plants. We are about 10% efficient. So if you eat food for a week, Sunday to Sunday, you literally leave 1 day's food on your body. The other 6 days went to keeping you warm. This has been studied all the way